Okay. We'll see if the sound works. Oh, I think this little thing says the sound's working. Pretty sure that's what that means. No. Okay. All right. Yeah. Yes. 10? Yeah. Yes. After we do 10, I'm gonna talk about 21 meme number. Okay. 9, 10. Big fat hen. Oh, you ever thought about that? Yeah. Okay. First step, 10. Let's quantify how much energy is stored in this system. Okay, how much energy? There's no numbers, it's all just symbols. So the mass is m, the spring constant is k, the spring is compressive distance, so we're using the letter d here. Okay, so we just gotta use that letter instead of x. And the height of the hill in the middle is the height of h. Cool beans? Mm-hmm. And then eventually we're gonna figure out, so we're gonna answer two questions. One is, let's stick to the first one, I guess, is how fast would the block be going? Top of the Humpty Dumpty. So what equation can I write that relates the state of the system here to the state of the system here? MGH. Yeah, so up here is going to be an MGH and also 1/2 mv squared, right? Yeah. But over here, all the energy is just stored in the spring. So to get this V, I'm going to write 1/2 k d squared. Usually I write 1/2 kx squared, but since the problem is defining the compression as d, then you're just going to use that letter instead. That makes sense? Mm-hmm. So that happens from time to time. You're doing physics problem, and they're like, oh, we're calling this quantity this letter. Then you're like, I usually use a different letter, but okay, it's fine. Anyway, so that's how much energy is stored in the spring. By the way, maybe a step before this is the spring energy turns into kinetic energy in gravity. Does that make sense? So spring energy is being converted into kinetic energy, movement, and potential energy, gravity potential. And v squared plus. Okay. Did I use the letter H correctly? That is what they call the height of the hill, right? Yeah. All right. So let's solve for velocity. Step 1. Okay, we can do that. Let's do 2 steps at once. Let's multiply everything by 2. And also, subtract this guy over. So multiply by 2, multiply everything by 2, and then subtract this from both sides so it looks like this. You feel okay about that? No questions? Okay. And then from there, 2 steps, divide by m. I think what I'll do is divide, when I divide by m, these both get divided by m. So this guy will cancel out, and this guy will have an m on bottom. So I'll have k d squared over m minus 2gh. And then I'm going to square root. That's pretty nice. There's that term that keeps coming up over and over again, right? 2gh. Oakley dokley? All right.
I have a question.
Yes.
What did you do there?
So I divided both sides by m. So I went like this.
Okay, that makes sense. I was like, what?
And so then this guy gets divided by m, and then when this guy gets divided by m, it just cancels out the m. Question B, will that be harder or easier than A? Easier, because So this is part A. For part B, the reason it's easier is, what do we not have to take into account down there? Potential, the gravitational potential energy. So for B, I'm just gonna basically talk about the transition. Here's the nice thing about energy. Energy gets to ignore the path taken. So I get to ignore this, right? It could have gone over a whole bunch of Humpty Dumptys. All I have to do is go, there was spring energy. That energy is conserved. So over here, I can say that that 1/2 kd squared is equal to the kinetic energy at point B. Does that make sense?
Mm-hmm.
So this one's a bit easier. You end up with K. We actually have gotten this result before, haven't we? So the twos cancel out. This was the answer that we got when we we found the velocity of the block right after it was released by a spring. It was question, someone help me out here. What question was that? It was like 7 or something like that. Yeah, one of the ones we did the other day. Are we okay with that? Are we okay algebraically from here to here?
Yeah.
How come the d squared turns into d? Oakley, and then the maximum height reached by the block. I'll do that here, I guess. Part C. Okay, so this is h max. So again, do I have to really pay attention to what happened here or here? Not really. I can just talk about how the energy, there was spring energy and then gravitational potential energy. So this one's just going to be 1/2 kd squared equals mg h max. And so does this result look familiar? I hope it does. This was the answer to a different question. Earlier, we asked the question of there was no hump, right? So the moral of the story here is, does the hump change much? You know, if we leveled out this hump so that it just went straight like this, the answer for this spot and this spot would be the exact same. The hump doesn't affect that. Okay. Okay. Important thing coming up. Let's see. How do I always manage to get these out of order? They should invent something that makes the papers all like stick together. So they can't like get out of order. That's a good name for it. That's a good name for it. What's up?
It'd be a great innovation.
Yeah.
Big money. But
Yes. Stonk up your trust fund with your royalties from that invention. Okay. 21. Meme number.
oh dear.
Oh, back to Okay, so this says a 20 kilogram block is released from rest from the top of the ramp of height 8 meters. And at the bottom of the ramp, we measure it to be traveling 10 meters per second. Okay. So this one gets right to the point. It says, well, how much energy was lost due to friction? So we got to be accountants. How much energy was there stored in the system before it started to slide? MGH. So I'm going to say the initial energy of the system was MGH. What does it come out to be?
1568.
All right. Hopefully there's no questions there. Straightforward calculation, right? So how much in a perfect world, or at least a frictionless world, frictionless, airless world, heatless world, how much energy would there be down here? 1568. So let's do the calculation. How much energy is there actually? Yeah. The final energy of the block is 1/2 mv squared, which would be 1,000. You okay about that? Exactly. So then how much energy was lost? Well, the energy lost would basically just be how much you started with, the initial, minus the final. So this minus this makes 568 joules. You feel okay about that? Okay. So then next, it says, if the block slid a distance of 16 meters along the ramp, what was the magnitude of the friction force exerted on the block by the ramp? So this kind of ties in with problem one from yesterday, number 19, right? So the work done by friction is equal to the friction force times the distance over which that force was exerted. Make sense? And of course, the work is going to tell you the change. The work done by friction would be, does that make sense? The work done by friction tells you how much energy friction has like sapped out of the system.
Yeah.
That's a big idea. Makes that hopefully makes sense to you. So this is gonna tell me the energy that was lost. Okay, so the force due to friction times the distance was 16 meters. Okay. And the energy lost we see is 568. Does that equation make sense? So this is how much work the friction did. This is the distance over which that force was exerted. So we're going to calculate the force, the friction force. What does that come out to be? Okay, great. Is class over? Oh,
yeah. Oh.
okay. We'll finish. I guess we'll finish the rest tomorrow. For C, you're gonna just real quick. You're gonna have to go. You know the friction force, and so for a ramp, it's mg cosine of theta times mu would give you that force. You got to be a little clever maybe to figure out what theta is, but use the fact that this is 8 and this is 16. Little. Yeah. Maybe inverse sine, figure out the angle. Yeah.